All right, well, welcome back, and let's jump into section 11.7. The PowerPoint was kind of locking up in presentation mode, so I'm going to use the slide viewer mode. Please let me know if it's large enough and if you're able to see everything all right. That feedback would be really helpful because I think this will be a smoother presentation. All right, so a couple of big ideas in 11.7 involve the counting principle and something called permutations. Very big ideas, and notice how they are different and how this section and the next section are different from what we've been focusing on. You'll notice that absent from this section is the word probability. You're not going to be asked to find probabilities. The focus is on calculating the number of ways a certain event could occur. So you'll be seeing the problems read differently. For example, you might see something that says, hey, how many passcodes of the letters A, B, C, and D are possible? Or how many ways could 5 horses finish a race? As opposed to, what's the probability of horse A winning? Remember, probability involves a ratio, and here we'll just be focusing on some mathematical tools to calculate the number of ways a certain event could occur. And then we'll return to probability and use those different tools to find probabilities. All right, here's a very simple example. You wake up in the morning and you're looking for how many different outfits are possible from 2 pair of pants and 3 shirts. So we can actually draw this out because it's a very small tree diagram. So let's say our 2 pair of pants are, say, our jeans and our favorite khakis. And we're going to combine that with, say, a red, white, and blue shirt. And we'll do that for each pair of pants. So we'll have our jeans and our red shirt, our jeans, and our white shirt, and our jeans, and our blue shirt. Our khaki with red, our khaki with white, and our khaki with blue. Well, in this case, you can actually see there are 6 possible 1, 2, 3, 4, 5, 6 pairs. Now, you might be thinking, well, I was thinking that was a possibility with 2 pair of pants and 3 shirts. Wouldn't that be really amazing and helpful if I could simply multiply 2 times 3 to get my 6 outcomes? Well, you'll be pleased to know that that's exactly what you're going to do. And this is called the fundamental counting principle. And the idea is, if you have a sequence of n events, in our case, it was 2 events. We were picking from pants and shirts. And if the first event can occur K1 ways, in our situation it was 2 pair of pants, so K1 would be 2. And the second event, which was choosing a shirt, call it K2. Again, don't get hung up on the notation. That could have been done 3 ways because there were 3 shirts. Now, notice it's very important. The fundamental counting principle always involves multiplication of successive events. If the sequence involves 3 events, you would multiply 3 options. However many choices you have, you multiply the number of choices. All right, and obviously we get 6. All right, so it doesn't matter how many events you're talking about. You multiply the choices, and that'll give you the total number of outcomes. Fundamental counting principle, very valuable. All right, here's an example involving passcodes. Passcodes are a big deal. Now, we're not going to be getting really long technical passcodes. It's going to keep them pretty simple. In this case, our passcode consists of 2 lowercase letters followed by 4 digits. When you say digits in this section and other sections, think numbers. All right? And individual digits, there are actually 10 choices because we'll have 0 through 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that's 10 choices. So don't forget about 0 as a choice for a single digit number. All right? All right, well, let's take a look at how many different passcodes are possible. Notice, didn't ask for the probability that someone's going to guess your passcode, but just how many are even possible. All right, this is definitely a fundamental counting principle, and I'll model it with like spots for the letters and numbers or digits. So first we'll take a look at the number of, these are your letters, and here are your 4 digits. And in this case, notice it says for part A, repetition of letters and digits is permitted. Okay? So, if repetition is permitted, how many choices do I have for the first letter? Well, there are 26, so I have 26 choices for my first letter. All right. And what about the next letter? Well, since repetition is permitted, I have 26 choices again. So there are 26 times 26 possible letters. I could pick A, and then A, B, and then B and Z, or T and Y. So I got a lot of choices. But we're going to combine that with 4 digits. Now remember, I've got 0 through 9, okay, 0 through 9 each time because repetition is permitted, right? Repetition is permitted. So I'm going to have 10 choices, and then since I can use any digit again, 10 choices, 10 choices, 10 choices. Grab your calculator and have your calculator handy for the rest of the lectures. I'm going to use it several times. Matter of fact, if you don't have your calculator, pause this video and go get your scientific calculator. I'm going to show you some buttons that you're going to have to be able to use on your calculator. Okay? So, 26 times 26 times 10 times 10 times 10 times 10. That is a pretty big number, 676,000. That's how many passcodes are possible in this situation. Okay? Okay. Letter B. In this case, repetition of letters is not permitted. Repetition is not permitted. Okay? All right. So let's keep that straight. Same exact scenario though. I'm doing 2 lowercase letters followed by 4 I think I will move this down here. Okay. All right. Well, how many lowercase letters are possible? Well, there's 26 letters, so I have 26 choices for my first letter in my passcode. But now repetition's not permitted, so I can't use whatever letter I just selected, so I only have 25 options left. All right, one less because repetition's not permitted. Kind of like conditional probability, right? If I don't put the card back in the deck, or if I don't put the marble back in the jar. All right, same exact idea. And you can see how probability is going to get worked into this later on. Now, with my digits, once again, remember, I start off, I have 0 through 9, which is 10 choices. But whichever number I use, I can't select that. So the next digit I pick, I have 9 options, followed by 8, and then 7. All right, so if you grab your calculator, 26 times 25 times 10 times 9 times 8 times 7, you should get, let me try that again. I missed a, Now this time you're going to have less because of the repetition not being allowed. 327, 600. Actually, oh my goodness, let's go back to this. I typed that number incorrectly, gang. That is not 676,000. It was 6,760,000. I got to read my calculator more carefully. Okay, so if you had that 6,760,000, you were correct. And this, let me erase him. Missed a decimal point. Don't do that. 3,276,000. All right. Notice it's almost half. Okay. Actually, it is half. So that repetition makes a big difference. Okay. All right. All right. Let's just keep working examples here. Still doing passcodes. Okay. In this case, your first letter must be a vowel. Okay, so you only have 5 choices. Repetition is not permitted. Okay, so let's go ahead and let's model this. So I've got my 2 letters, all right, followed by my 4 digits. All right, so one at a time here. I've got 5 vowels and repetition of letters and digits is not permitted. So my second letter, I only have how many choices? 4, that's right. And this is interesting, and this happens quite a lot in situations. I mean, when you make your passcodes, they always have certain restrictions, right? Well, this one says the first digit cannot be a 0. Well, normally you've got 0 through 9 as your choices. Now you have 1 through 9. So instead of 10 choices, you have 9 choices. Okay? Now, this is tricky because your second digit, now 0 is in play. But whatever digit you chose for the previous digit can't be used. So normally we have 10 choices, 0 through 9. We couldn't use 0 for the first time, so say we picked 1. Well, now 0 is in play for the second digit because it just says the first digit cannot be 0. So hopefully you arrived at the fact that you now have 9 choices still because I can use 0. I just can't use whatever number I chose for the previous digit. And now since I can't have any repetition from here on out, I have 8 choices followed by 7 choices. All right? And that is 90,720. All right? So if that was a little tricky, just pause the video and go back and watch that again. But I couldn't use 0, so I had 1 through 9. Whichever digit I picked for the first digit, I couldn't pick for the second one, but I could use 0. And 0 was in play also for the last 2. Okay? All right. Now here's a pretty common situation involving probability. Involving arrangements or how many ways an outcome can occur. You got 5 race cars, and we'll call them A, B, C, and D, and E, just for this problem. How many different ways could they finish? Obviously, in the world of betting, they're very concerned with the number of possibilities. The more race cars, the more horses, that lessens the chance of any one winning. Okay? So, we can model this with the fundamental counting principle, and it would look like such. I've got 5 possible outcomes for first, second, third, fourth, and fifth. And since these are successive events, okay, assuming all 5 cars finish, then we're using the fundamental counting principle and we're multiplying the number of ways each spot could be determined. Well, when you start the race, there are 5, hey, how about that little stardust? There are 5 different choices for first place. All 5 cars have a chance to win. Now, once first place is determined, now there's 4 cars left for third, and 4 cars left for fourth, 3 cars left for third, 2 cars left for second, and 1 car left for fifth. Well, 5 times 4 times 3 times 2 is 120 possible ways that could happen. Okay? Well, this idea of multiplying successively lower numbers is so common in mathematics that they came up with a symbol that would actually perform this calculation. Arranging things, looking at different orders of finish, very, very common scenario. So, with calculators, the symbol is called, well, that's coming, actually, hold on. But this idea of sequences of events, okay, or arrangements, we just had an arrangement of 5 cars finishing. This is called a permutation. And this is a really big idea as we finish up this chapter. The next idea, next section is called combinations, and you've got to keep combinations and permutations straight, okay? So permutations, I want you to think arrangements. You are arranging things and the order would make a difference. Order of finish, things lining up, people lining up in a line. Okay, so not that it makes a difference to you personally, but that it would make a difference in the race or make a difference in the arrangement of people. So permutations, when the problem involves arrangements, think permutations, okay? So the arrangement of n distinct objects in a specific order is called a permutation. So the previous problem, there were 120 permutations of those race cars, 120 different ways they could finish, okay? Okay, so here's the requirements. Each item can be used only once, and these actually make sense. You can't have the same car finish first and second, right? So each item can be used only once. The order of the arrangements makes a difference. Again, not to you personally, but the results are different. It would be a different race. Okay, if the cars finish in a different order, then it would be a different outcome. That's all that means. And the number of permutations of distinct objects using all the objects is n factorial. New symbol, the exclamation point. I'm not being emphatic. That is actually the symbol that mathematicians used to describe this pattern of multiplying by smaller numbers, 5, 4, 3, 2, 1, or 6, 5, 4, 3, 2, 1. Okay? All right, let's talk about that. So here we go. And that's what this factorial notation means. It just means you multiply by one less number each time. Okay? 3 times 2 times 1. Okay? You multiply by one less successive numbers. That's called a factorial, and what we just did with the race cars was 5 factorial. And I'll show you how to do that on your calculator because it has all that information already stored, which is actually pretty cool. Okay? Just some things to keep track of. It might be kind of odd, but 0 factorial is actually defined as 1. Okay? We don't need to get into why, and it might not even be a big issue in this class, but just some basic definitions about this new idea. Okay, so the exclamation point just like a square root, it has an operation in mathematics. So 1 factorial is 1, because there's nothing else to multiply it by. 2 factorial is 2 times 1. 3 factorial, notice how the numbers get smaller each time. 4 factorial, okay? And the one we did earlier was 5 factorial, and we got 120. These numbers actually get pretty large pretty quickly. Factorials grow quicker than exponentials do. So at some point, your calculator will not be able to, like, none of your calculators can do 20 factorial. 20 times 19 times 18 times 70. That number is huge. Okay? Okay. So just a few more things about factorials. Again, not that this is a big deal in this class, but if you take a class in stats, you might come across some of this. 5 factorial was our race car problem. Okay? And you could actually stop the factorial anywhere in the process. In other words, 5 times 4 factorial would be 5 times 4. I mean, it would actually look like this. It'd be 5, and then you would do 4 factorial, 4, 3, 2, 1. So it's 2 different ways to write the same problem. I could write 5 factorial as 5 times 4 times 3 factorial. I can stop it anywhere as I want in the process, and it means the same number. Okay? If you divide a factorial by itself, you're going to get 1. That should be kind of logical. All right, so grab your calculator, and let me show you where the factorial button is. Okay? If you have to pause the video to go get it, go ahead, and then resume when you have your calculator. Okay. Now, this looks a little bit like a TI 8384, so that'll be helpful, but most of you will be finding, you'll all be looking for a PRB menu, okay? PRB means probability. So I'll give you a second to look your calculator over. It might be, you might have to use a second feature, but you're looking for a PRB menu. For the TI people, it's math, and then see the PRB right there, PRB, and look at number 4. There's your factorial, okay? Now, the way that you want to do this is on your home screen, type the number that you want to take the factorial of. So we would type 5. Number 5 factorial was 120, so we'll do 5, and then math, find your PRB, and then hit the factorial, and there you go. All right? So I think in the slide you were asked to do 8 factorial, so let's try 8 factorial. So remember how to do that? So hit the 8, hit the number, and then go find your PRB menu. For the TI people, it's math, PRB, and then number 4. So see how they get really big? So 40,320. Okay, so for A, 8 factorial was 40,320. Now why don't you go ahead and go try B on your calculator. So 12 factorial divided by 10 factorial. So that would be 12 factorial, math, PRB, factorial, divided by 10, math, PRB, factorial. Okay? 132. Not as large as you maybe were thinking. Now, just so you know, so this was 132. I could have rewritten this as 12 times 11 times 10 factorial. And what do you notice? That might be a way to handle some larger numbers, because maybe things would cancel. And what do you think 12 times 11 is? Yep, 132. So there's some cool number properties of factorials, but you won't need too many of them for this class. Okay? All right, let's resume. Excuse me. So in 7 of the 10 years from 1998 to 2007, the 5 Major League Baseball teams in the American League East finished in the exact same order. Imagine betting on that. New York, Boston, Toronto, Baltimore, Tampa Bay. Just how unusual is this? Well, let's find the number of possible finishing orders for these 5 teams. Now, you got to start asking yourself, does this problem involve a permutation? Well, can each team only finish in one place? I mean, New York can't finish first and second, right? So each team gets used once, so check that box. Does the order make a difference? Well, yes, because if the team finishes in a different spot, then they might make the playoffs, they might not. So this is definitely an arrangement. The order makes a difference. All right, so what I like to do is I like to draw spaces for my 5. All right, let's try to move that down a little bit. And I think I might want to change the size of the pen. All right. All right. So how many choices do I have for the first place? Well, there's 5 teams, right? 1, 2, 3, 4, 5. 5 teams. So I have 5 choices for the first place, and then I only have 4 teams left, and then 3 teams left, and then 2 teams, and then 1 team. So this is definitely 5 factorial. But I want you to notice that the fundamental counting principle also works for permutations. Okay? Don't forget the fundamental counting principle. So you have some options moving forward. And the fundamental counting principle will be very useful on some problems where the permutation just can't, the permutation itself can't take into account restrictions, okay? Whereas the fundamental counting principle can. We saw that for the passcodes. So either way, there are 120 ways that these teams can finish. Isn't that amazing that for 7 years they finished in the exact same order? That is amazing. It's just too bad Tampa Bay was last. But not always last. Not in, I think it was 2008, right? All right. Oh, well, I already mentioned this, but we could have done the factorial, right? Because it's involving permutations, which is arrangements. But you also could have been thinking about the fundamental counting principle. So just to show that again, 5, 4, 3, 2, 1. They both give an answer of 120 possible or 120 permutations. You can think about that word as being arrangements. Okay? All right. Say you own a car dealership and you want to line your cars up along the road and try to catch people's attention coming by. So how many different ways can 7 different cars be arranged next to one another? Why don't you pause the video, work it out, practice with your calculator. Remember, ask yourself, is this a permutation problem? And then start the video up again, and let's see if we agree. Okay? Go ahead and work it out. Okay, so coming back, you should have had 7 spots lined up for your cars. Now, this is using which property? This is the fundamental counting principle, right? You're using all 7 cars, and the numbers are decreasing by 1. So this is a special arrangement, right? This is actually a permutation. So you could have figured it out this way. You could have got, I have 7 choices for the first spot in my car lot. Then I have 6, and then I have 5 choices left. And then 4, 3, 2, 1. Okay? Or once you realize that they were decreasing by 1 each time, you're going to go, hey, this is the factorial. And either way, you would get 7 math probability, boom, 7 factorial, 50-40, 50-40. So that's a great way for a car dealer to spend their afternoon, is figuring out how they want to arrange 7 cars, right? All right. Hopefully you got that. Let's check this out. This is interesting because now you're not using all of the options. You're not using all the cars or all the horses, or in this case, all the letters. You're going to be arranging 3 out of the 5. Interesting. So this is definitely not like 5 factorial. That wouldn't work because that would be too many, right? Let's take a look at this. So let's just say we have these 5 letters, A, B, C, D, E. How many distinct ways can 3 letters be selected and arranged if repetition is not allowed? All right. So let's draw ourselves, we've got 3 letters. Since there's successive choices, I multiply them. So I'm actually using the fundamental counting principle this time. So let's see. So I would say I've got how many choices though? Even though I'm only arranging 3 letters, I have how many to pick from? 5, that's right. Okay, so I have 5 choices, and then 4 choices, and then 3 choices. So notice this doesn't go all the way down to 1. This is not 5 times 4 times 3 times 2 times 1. And this is where the factorial can't take this situation into account. This required the fundamental counting principle. So please keep that idea in mind as you're working your homework problems. Now, very interesting though, there is another way that you could do this. So check this out. And this will actually lead us to a pretty important formula for this section, okay? What if you decided to keep on going and you multiplied times 2 times 1? You would say, well, wait a second, you multiplied by too much, and you'd be exactly right. So the way to get back to the answer, let's calculate the answer. It was 5 times 4 times 3. So the actual answer was 60. Okay, so let's write that down over here. So the actual answer was 60. And now, do you remember what's 5 times 4 times 3 times 2 times 1? It's 120, right? I made the number too large. But wait, what if I divided by the same thing that I just multiplied by? In other words, what if I just divided by 2 times 1? Wouldn't that work? When I multiply and divide by the same thing, don't they cancel out? Well, yeah, this would work. This would give me 120 divided by 2, or 60. Okay? So you might be thinking, well, what does that accomplish? Well, if you think about it, that actually accomplished something pretty clever. Because now, how could I rewrite the top? What is 5 times 4 times 3 times 2 times 1? Well, that is 5 factorial. And what is 2 times 1? 2 factorial. So I could actually use factorials on this problem. The only thing is, we've got to think about what exactly or where did this come from? Is there anything special about this 2 factorial? Is it going to be 2 factorial every problem? Well, no, of course not. What this is these are the 2 letters that didn't get used. These are the leftovers, okay? Or 5, I had 5 to pick from, and I only picked 3. What's 5 minus 3? 2. So the bottom could always be the ones that aren't getting used. Or in this case, it'd be 5 minus 3. Okay? That actually is a very important formula for us. Okay? Definitely want to keep track of this. So a formula for finding permutations of n objects taken r at a time. That was our previous problem. We had 5 objects, 5 letters, taken 3 at a time. Now what this 60 actually represents, if you think about it, would be like the letters A, B, and D, or C, B, and A. They're three letter arrangements. Okay, there's ABC and CBA would be 2 different arrangements, right? Or permutations. So there's 60 different 3-letter arrangements that I get from 5 letters. That's what the 60 means. 60 different arrangements of 3 letters picking from 5. Okay? All right. So n is always the larger number. And the way that you say this formula, it's NPR, or I'm picking R from N. So in the previous problem, my N was 5 and my R was 3, right? I had 5 letters and I was picking 3. So the previous problem could be written like this. Probability of 5, not probability, permutations. How many different arrangements of 3 letters selecting from 5? And there is a button on your calculator. Okay? So get your calculator back out. Pause the video if you have to. But get the calculator back out and join me at your calculator, and we're going to figure out what 5p3 is. Okay? All right. So it's going to be back under your probability menu. So go Math, Probability, and look at number 2, NPR. NPR. So most calculators will give you a screen that allows you to fill in the numbers in the spots. So I'm going to put a 5, and then I need to arrow over to the 3. Okay? And hit enter. And there's my 60 again. Now, some of the calculators, you're going to have to do this. You're going to have to type the 5, go find your probability menu, okay? Hit the NPR. See, it won't let me do it. It won't let me do it. But yours will look like this when you type in your calculator. Yours will look like this. Depending on the calculator that you have, yours will have to look like this. 5, and then it'll be NPR3. So that's how it might look on your calculator. But again, just try this one because you're supposed to get 60 on the problem that we just did on this one. Okay? So just try it until you can make your calculator produce 60. All right? All right. Again, I wish I could be there with you. If you're really struggling, don't hesitate to send me an email, and we'll try to figure something out, okay? All right, so let's try this problem. How many different batting orders are possible for a Little League team if you can choose any 9 of the Little Sluggers from the 13 team members? So you got a 13 players on a Little League. You can choose 9 for a batting order. All right, for a batting order. And you need to ask yourself, is this problem different from the others we have done? Well, we're not picking all 13, so it's definitely not 13 factorial. That would be if we were using all 13 members, okay? And that number might be at the extent of your calculator. I'm actually plugging in right now. That's a big number. That's like 6 billion, I believe. 6 billion, yeah, that's a big number. Okay. But we're not using all 13, okay? So there are two ways to do this problem. The first way would be with the fundamental counting principle, okay? Meaning I've got 9 spots in my batting order. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that makes up one batting order. So all of these are successive, okay? Now, if we're going to do it this way, how many choices do I have for leadoff or the first spot in the batting order? Or let me ask you, hey, does this seem like it would be permutations? If I arrange the Little League players in a different order, will I get a different batting order? It's like, yeah, definitely. And if you know anything about baseball, it definitely matters who you put where. You want your better players up near the front so they bat more often. So this is definitely a permutation. The order makes a difference. We are arranging the players in an order that makes a difference. Okay, so how many choices do I have for the first spot? How many players on the team? 13. Now, obviously I can't have the same player bat in more than one spot. That's not even allowed. So once I pick a player for the first spot, I then have how many choices left? 12, right? And then I have 11, and then 10, 9, 8, 7, 6, and 5. Now, I didn't go all the way to 1, so this is not 13 factorial. Now, we just talked about the fact that we have the permutation formula, which is exactly what we do when we don't use all the items, right? I have, for our problem, I have 13 to pick from, and I'm picking 9. So how many are not getting used? 4. And that is what our formula is, right? Okay, it's the total number on the top. So the top is the total. And then the bottom is the items not getting used. All right, and the different arrangements of them. Remember, the factorial basically means you're arranging things. Okay? All right, so how many batting orders are possible? Well, we can do it either way. I didn't go to the calculator yet, but let's check it. So 13 factorial over 13 minus 9 factorial. And you can think about the 4 as being the four players that don't get used. Okay? So go ahead, pause the video, grab your calculator, and try this both ways and compare your answers and come right back. Okay, so I'm going to go to the calculator and let's see. So 13 math PRB factorial divided by 4 math PRB factorial. Whoa, look at all that. That is a big number. 259 million. Wow, that's a lot of batting orders. Okay. So I'm going to have to do that on my calculators because I can't remember that number. So 13 divided by 4. All right, here we go. And the answer is 259, 459, 200, 259 million different ways you can arrange the guys. Again, because you're picking 9, and then you can arrange all those 9 in a different way. There are 259 arrangements, okay? 9-person arrangements. It's mind-boggling, okay? All right. I hope you're doing great. I hope you're hanging in there. We're almost done. A few more slides, okay? All right. I would like you to solve this one. A NASCAR race has 18 cars entered. If all 18 cars finish the race, and how many ways can the top 3, all right, there we go, top 3 cars finish? Okay, so pause the video, think about what we've been working on, and come back and see if you agree with my work. Ask yourself all the questions. Is it a permutation? Is there arrangements involved? Okay? All right. All right, you're back. Now, you could have done this problem 2 different ways. You could have used the fundamental counting principle, okay, which would mean we're looking at 3 orders of finish, just first, second, and third. That's our event, okay? And each car can only finish in one place, and the order makes a difference, so it's definitely an arrangement, a permutation, okay? So how many choices, if all the cars finish, how many choices for the first, Well, 18 cars finished, so there's 18 choices for the first place. Now, once a car finishes first, there's how many left? 17, and then 16. So 18 times 17 times 16, only 4,896, okay? And that's because you're only looking for first through third, not that many different slots. Now, hopefully, you were thinking that this could also be the permutation formula. Okay. And there was 18 cars, and you're looking for 3. You're picking 3 cars to finish first, second, and third. So 15 cars do not finish. Well, they don't finish. They don't place. Okay. So again, now as far as showing your work on the homework, this is all you've got to do is give me this, and then the answer. You don't need to work it all out. Okay. But again, what's the formula doing? It's taking a look at all the possible finishes, and it's subtracting out the 15 cars that don't get used. This is what's going on in your calculator. So if you go ahead and try that on your calculator, you of course will get 4,896. Okay, so you can go either way. And again, for showing your work, just write out the formula, and then you could go right to the answer. But make sure that you do give me the answer. Okay? All right. So, what about if there are repeated objects? Well, let's think about this. Let's just take a simple example involving the name Anna. And I say, hey, how many arrangements are there of the letters? Okay. Well, if you start writing them out, and you say, for example, A, N, N, A, and A, N, N, A, and you say, well, you can't count those. That's the same word. It's like, well, sorta. What if I jokingly said to you, yeah, but I switched the ends? You'd say, oh, well, that's silly. Or I could say, hey, I switched the A's, or I switched the N's. Well, obviously you can't tell. So when there's repetition, there's going to be a lot fewer new arrangements, okay? And anytime you want to have less of something, you end up dividing, okay? So for this problem, basically what you do is you start off with the total number, okay? So the answer is 4 factorial, but then you're going to divide by the number of repetitions. So you say, okay, well, what repetitions? Well, I have 2 A's, okay? So I have 2, and that's going to be I can't really fit that in. So that's the A's times my N's. So I got to divide that out. Now, to make sure that your calculator does that correctly, put parentheses around the bottom. Okay, go ahead and try that. Go ahead and try that and see if you can make your calculator do that. Okay, so if you kind of follow along with me, it would look something like this. So you'd go 4 math PRB, okay, divided by, and again, depending on the calculator, the parentheses might not be necessary, but you'll never get the wrong answer if you use parentheses at the appropriate place. Okay, so that, notice, is only 6. So the repetition makes a big difference. It reduces the number of arrangements dramatically because there's not as many because of the repetition. Okay, so try this idea with the word Mississippi. Okay, so there's 11 letters. There's 11 letters, but obviously there's not 11 factorial ways to do this because there's lots of repetition. So go ahead, pause the video, see if you can write the statement that would do that, and then go on your calculator and try it. Okay, so go ahead and pause and then start it up again. Okay, so let's see. So we know there's 11 total, but because there's repetition and a lot of repetition, okay, I've got to divide out. I've got to divide out all the repeated letters. So let's start with the I's. 1, 2, 3. So there's 4 I's. And I got to do 4 factorial because it's all the different places the I's could appear in the words that would not be distinguishably different. It'd look the same. So I have to divide out by the number of places the I's could appear. Now that's not the only place. I've also got S's. I've got 4 S's. Okay. And I've got 2 P's. Okay, so there you go. 11 factorial divided by 4 factorial times 4 factorial times 2 factorial. And be careful, as it says down below, you can't do like 4 times 4 times 2. 4 times 4 is 16, times 2 is 32. That is definitely not the same as 32. 32 factorial is a huge number that your calculator probably could not even do. So let's jump to the calculators and let's do this. Go ahead. I asked you to already do it, so let me just kind of quickly do this guy, and let's see what we get. So 11 factorial divided by 4 factorial times 4 factorial times 2 factorial. Goodness. All right. A lot of button pushing. I got 34,650. And I hope you did too. Okay? Long section. A lot of ideas. Please don't hesitate to watch some things twice. Remember, your homework is due every Wednesday night. And I've already had students uploading it. It seems to be going well. And I'll be working on the next lectures. I'll be posting them sometime over this week for you to watch before next week when the homework is due again next Wednesday. Okay? All right, just keep watching your emails and check my courses for updates and informations and announcements. Okay? Great. Take care. Hope you're doing great. on this. Hope this lecture went